Hello, everybody. I'm delighted to share with you our work in creating new materials for climate and in using AI to accelerate discovery. This work is done in close collaboration with our CACS colleagues who are listed here on the right: Dr. Majid, Dr. Arwa, Dr. Marwan, Dr. Hanan, Dr. Wala, and Dr. Nahla, as well as Dr. Al-Batul. It has been such a pleasure to have this collaboration, and it's been quite fruitful, as you will see shortly. Let me begin by showing the following NASA images. These are images indicating the concentration of CO2 from January 215 until 220. You'll see here the concentration of CO2 in the atmosphere from 392 ppm going all the way to the yellow, where it's above 400 ppm. So watch for the yellow to creep in, indicating progressively higher and higher concentrations of carbon dioxide in the atmosphere. And that's only in the last about 7 years or so. It goes up to February of, I guess, February of 2022. So we are emitting between 40 to 50 gigatons of carbon dioxide every year. And right now, the amount of extra carbon that has been put in the air as a result of industrial activities since the Industrial Revolution amounts to almost 1,100 gigatons of CO2. This is the extra carbon dioxide that I'll show you later how we are working with CACs to remove it from the air. So here in the United States, it's been the case that for the last 3 years, each year has been a record heat year. So clearly, carbon dioxide is changing our climate, and weather events are becoming more and more intense. This is affecting the lives of people everywhere, as well as the livelihoods of a lot of people, especially in the developing world. This is a picture of Malibu burning, one of the most beautiful places in California, perhaps in the United States, is burning with great intensity. This is the result of carbon dioxide in the atmosphere and the climate change that comes with it. Another topic that I will be discussing, and is also being done collaboratively with our CACS colleagues, is the global water stress. And this map shows you in progressively red colors the intensity with which we will be experiencing water stress between now and the year 2040. By the year 2040, the UN projects that almost 5 billion people on our planet will be experiencing water stress. And almost 1/4 of our world population will be living in a water crisis. And that means that they will not have enough water to sustain themselves. You'll see here in the map places like London or Belgium, places that you and I think are highly watered, will be experiencing water stress because we are using more underground water than is being replenished. That is true also in much of the United States, as well as many parts of Saudi Arabia. So water is an ongoing challenge. Here in near California, in Nevada or northern Arizona, there is a dam, one of the largest dams in North America. It's called the Hoover Dam. And you can see the level of water in the Hoover Dam from 1983 going down in 2003, and then now going dangerously low in 2022, shown here. This dam supplies almost 16 million people with water. So we are in a really dangerous situation. So as a chemist, we know the molecules that we need to be working with to address the problem. And these are hydrogen. They are some of the smallest molecules in chemistry. Hydrogen, we need to be able to store hydrogen because it burns cleanly with only water as a byproduct. We need to utilize methane. Methane is 50% cleaner than petroleum. And we already know how to, using our materials, we already know how to store methane in an economical way and use it for transportation. We need to take carbon dioxide out of the air to clean the air. No matter what we do in terms of reducing the use of fossil fuels, we still need to take that extra carbon dioxide from the air because it is the material that is causing the climate problem. We also, I will show you how we can take water from air and create a new source of water, new source of drinking water from air. Well, chemists have for a long time been great at navigating the periodic table. And one of the outcomes of being able to work in chemistry has been making pharmaceuticals. So the question that we asked is, how can we take molecules almost like Legos and stitch them together to make different structures? And the result of this has been what I call reticular chemistry. And that's the chemistry of linking molecular building blocks by strong bonds to make crystalline extended structures. Molecular building blocks, like using molecules like Legos and stitching them together by strong bonds to make robust materials that are going to be in a power plant, preventing CO2 from going into the air year after year after year without having to be replenished, or taking CO2 out of the air for many, many years before you have to maintain the materials. Crystalline, so that the hallmark of reticular chemistry is that we can make crystals and we can characterize them and modify them on the atomic level. The result of reticular chemistry has been metal organic frameworks. These are porous structures made from very strong metal carboxylate bonds, charged organics, to make porous structures. The yellow ball here you see is the space within which one can compact hydrogen or carbon dioxide or other gases that I have discussed already. Another result of reticular chemistry has been covalent organic frameworks, which we discovered back in 2005. These are all organic structures, and here they are stitched by very strong covalent bonds. There are other materials I will not discuss here that have been the result of our work in reticular chemistry. I want to focus on MOFs and COFs to show you how they're addressing the climate problem, and then how we're using AI to accelerate further discoveries. So the strong bond approach and the Lego, the building block approach, is the key to this chemistry. I want to show, for some of you who are not familiar with MOFs, that MOFs look like, to the naked eye, they look like baby powder, or they look like granulated sugar. And in this movie, it shows that when you zoom in on just one granule, you'll find that on the atomic level, that it's riddled with holes. And it's in these holes that gases that would fill very large volume could be compacted within the pores, as you see here. So in many ways, the inside of the material, or the inside of the granule, has much larger volume than the outside, and they act like magnets, bringing in gases and compacting those gases within the pores. That's really how MOFs work, or how these reticular materials work. Here's a structure that has a surface area of 6,400 meters square per gram. And that's because, as you see, the inside is very open, and you can see it's like a scaffolding onto which gases could be attracted and concentrated. So in 1 gram of material, you have a footage of an entire football field, and that's what makes them special for working with those 4 small molecules that I showed earlier: hydrogen, methane, CO2, and water. Now, we have, through our work with BASF, shown that in fact MOFs could be scaled up to multi-ton quantities. And here's one of the early MOFs. You can see it looks like basically a white powder. This one is made from zinc, and therefore it has a white appearance. So the chemistry, if you can think up a structure you want to make, you can make it. And not only can you make it with precision, but also you could vary its components, both the organic components and the metal components. And therefore, in so doing, you're also designing the porosity. You're designing not just the size and geometry of the pores, but also their chemical environment. So reticular chemistry is an infinite frontier. That's what makes it so appealing to AI studies. And as many of you know, MOFs and COFs are being pursued in over 100 countries in many fields, including not just clean water and clean energy, but also biotechnology and medicine. So let's talk about carbon capture. Here, the problem could be divided into two parts. The problem of taking CO2 out of the air, where it is, you have one CO2 molecule for each 2,500 molecules in the air, so you have to pluck it out of the air selectively, or in other words, it's 0.04% by volume of the air. Or from point sources, where if you burn natural gas, you're emitting about 5% CO2 by volume. Or if you're burning coal or petroleum, the CO2 levels could go up to 16% by volume of the flue gas. So these are two problems that we need to be able to address. And I'll show you how MOFs and COFs have been able to do this. So here are the minimum requirements for a carbon capture material. One is that they need to have high capacity. Well, I think MOFs and COFs are okay for that because they have extremely high surface area. You need to have high selectivity. Well, we can modify the interior of the MOF or COF so that it does only seek out CO2 out of the air in a selective manner. They need to be water stable. They need to be oxidatively stable, and they need to be cyclable. They also, once you bring in the CO2 or water into the pores, you need to regenerate the material without having to heat it up to very high temperatures. So the lower the temperature of regeneration, the better off you're going to be, because the lower energy the system is going to require. And it needs to be scalable. So this is a tall order for materials, but it's not beyond the reach of reticular chemistry. So there are many materials that are being pursued out there, ranging from aqueous amines to carbon to zeolites to organic resins and silica, metal hydroxides, also MOFs and COFs. And I want to show you today that the results on MOFs and COFs look extremely good, while the other materials suffer from one or more issues that prevent them from having wide-scale applications. But let me show you the results from MOFs. So here is a MOF that was made based on our chemistry from at the University of Calgary by Professor George Shimizu's group. This MOF is called CAF20. It's a zinc carboxylate imidazolate COF, and this was published back in 2021. It's being scaled up and is being tested in pilot plants already, several pilot plants. So this MOF is very special because it takes up a lot of CO2, so 2 to 4 millimole of CO2 per gram, and it's been cycling over 450,000 cycles. The key here is that it's great for point sources because it's taking CO2 out of more concentrated, higher concentration, as in cement plants. So this MOF is already being scaled up by BASF, as you would be able to see in this media news release, is that BASF is scaling up this MOF to 100-ton quantities to be placed in 3 pilots in Canada, where it's already capturing CO2 from cement plants. So this is a big blockbuster, I would say, application for MOF, and it is already deployed to prevent CO2 from reaching the atmosphere. And this is especially true for these cement plants where the CO2 concentration in the flue is much higher than it is in the air. And so this material is really applicable to this application. So this is a very exciting result. But MOFs in general will not work for DAC, for CO2 capture from air. And the reason for that is that to do CO2 capture from air, you need the use of amines. And amines are basic, and most MOFs could not withstand long-term cycling in basic media. So, and this is basically the experiment that one needs to try when you have a material. Basically, you're exposing your MOF or COF to a stream of air that has CO2 in it. Obviously, this is 420 ppm, just like it is in an average in the air, and see whether the material can scrub the CO2 out of the air and make air that does not have CO2 in it. And there, if you want to do these DAC, you need to go to COFs. And in COFs, you see here back in 2019, we had a breakthrough in that we can make COFs that are made from some of the strongest bonds known in chemistry, carbon-carbon bonds, carbon-carbon double bonds, and carbon-nitrogen double bonds. And you can see here on the right the stability of this material in highly concentrated HCl, in acidic media, in concentrated basic media, as well as corrosive media such as N-butyllithium, methyllithium. This is the kind of stability that made us really excited about addressing a challenging problem such as CO2 capture from air. And accordingly, we took that chemistry and, without describing the details of it, and attached polymeric amine units onto the backbone of that COF. You can see here the amines in blue. And for each amine, you're going to be able to capture a CO2 molecule. And without these amines, you cannot capture CO2 from air. So these are needed. The material I showed you is stable under varying severe conditions in acid and base and corrosive media. So our anticipation when we did this was that this material would really be durable for CO2 capture from air. This has been really a beautiful study jointly with CACS that has recently been published in Nature and widely covered in the press because it's basically a game changer in the world of capturing CO2 from air. So this is the result. And we didn't waste any time in testing the material and its performance in using Berkeley outdoor air. So we just piped in the air from the atmosphere of Berkeley into the material. And this is the CO2 uptake. You see the CO2 uptake here at the bottom over 100 cycles. And it goes up and down because it's influenced by the amount of water in the air. Okay. This is up here in red is the amount of CO2 in the air. In the middle, you have the amount of humidity in the air. And you see here at the bottom, the bar diagram, the CO2 uptake. And the CO2 uptake scales with the amount of humidity in the air. But if you pick one humidity, you will find that it's exactly the same uptake throughout the process of doing 100 cycles. So this was a very exciting discovery because this is a durability that we have not seen in other materials. And so it was very clear that COFs are really the forerunners in solving the CO2 capture problem from air. This plot shows you how at approximately the same humidity level, you see the maintenance of CO2 capture level. And that's the sort of stability that you need to be able to cycle for many, many years without having to replenish the material. These are the different parameters that we look at. For DAC, the capacity is 2 millimoles of CO2 per gram, way above the minimum requirements for commercialization. It also could be applied for point sources, as you see here, with significant uptake of CO2 per gram of material. So how does this look like at scale? Okay, let's now review. We have 11, as I mentioned, about 11 gigatons of extra CO2 in the air that we need to capture. This is the extra CO2 that we put into the air as a result of the industrial revolution. Okay, this is for the last 100 years, we put in that much CO2 into the air. Now, for this cough, even at its capacity of 2 millimole of CO2 per gram of cough, we can cycle about 10 minutes per cycle. Okay, so with these parameters, I can say the following. If I have a plant that employs 100,000 tons of cough, it will capture half a gigaton of CO2 per year. Okay, and if I put such a plant in every city that has a 1 million population or more, that's about 700 cities around the world. It's going to take us less than 3.5 years to take that CO2 out of the air. Okay, not bad. The scale, obviously, this is a large scale, but it's not beyond the reach of our chemical industry. Chemical industry already produces 200 million tons of, let's say, sulfuric acid every year. So the scale is appropriate. If obviously, if you don't want to take it out in 3.5 years, I think we should, because it's harming our planet. If you just want to put those plants into 200 cities that have 2 million population or greater in China, US, and Europe, it will take 11 years. So what I'm trying to say here is that the scientific challenge of capturing CO2 from air is solved. It needs to be scaled. In order to be scaled, we need to start thinking in a different way, and we need industry to focus on this, society and industry to focus on this problem. But we have the material, and we can address this challenge within a short period of time. And think about the following scenario, is that if we can double this uptake, which we are within, is within our reach, then all these numbers are cut in half. Okay, either the plants don't have to deploy 100,000 tons, but 50,000 tons, or the time takes to capture the CO2 is cut in half. So that's the beauty of the chemistry that we have developed. But what I want to say here in conclusion to this section of my talk is that the problem of CO2 capture from air in the lab, as well as demonstrating it in real air, is solved. The rest is for this to be scaled up. The installations are already in place to deploy such materials and start capturing CO2 from air, as is being done with MOFs at point sources. So the next application that I want to also share with you is harvesting water from air. There's plenty of water in the air. We have as much water in the air as we have in rivers on our planet. There's almost 1,300 or 13,000 cubic kilometers of water in the air at any one time. And we want to use MOFs and COFs to extract that water from air and generate water anywhere in the world at any time of the year. And the problem with being able to capture water from air is that in a typical city, let's say in an arid environment, and during the summer, you might, like in a Mediterranean city, you might have temperature of 30 degrees C and a relative humidity of 20%. To take water out of that air, you need to cool it down to 4 degrees Celsius, which is very impractical because it requires, and not economical because it requires a lot of energy. Now imagine that I use the MOF to concentrate the water, and in a closed box, upon exposure to sunlight, water will come out of the pores and I create a humidity. So in a way, I've taken arid air and made it tropical air. And in order to take water out of tropical air, I have to go from C to D or reduce the temperature by a few degrees Celsius to get the water out. And that's exactly how the MOF works. So here's the MOF. It's made from zinc triazole or diazole, perazolate, it's an aluminum, it's not a zinc, it's an aluminum perazolate MOF. And you see here on the right, the hydrophilic regions where water is going to be binding, and next to hydrophobic regions, these will reject water. And this acceptance rejection of water allows you to modulate in the pores the binding energy of water and the temperature at which you can remove the water. But you see here in this isotherm that this material already could take up water from relative humidity of 5%. Most water is taken up at a humidity of 10%. Now, if this material works, as you see here, at low humidity, it certainly would work much better at all the higher humidity. So we don't need to necessarily make a new MOF for each humidity level. It's the minimum humidity level is 5% here. So anything higher than 5%, this MOF would work for that. And this is how the MOF takes up water. I'm going to just extract one pore and slice it to show you where the water molecules reside inside the structure. And you'll see water going into the hydrophilic sites, first water, second water, third water, and a fourth water. Now, they will bridge over the hydrophobic sites, okay? Driven by hydrogen bonds between the water molecules. And as I mentioned, because of the hydrophobic tiling of these pores, you're able to remove the water, in this case, at 50 degrees Celsius. So just by exposing the material to sunlight in a closed system, you're able to take the water out, as these students have demonstrated by making a device that they tested in Death Valley. Here's a device that's made from pancakes of MOF. And during the night, the MOF is exposed to air. During the day, the device is closed down. It heats up, and then water comes out. This is just a demonstration of how powerful the MOF is in taking water out of even the most arid air. Okay.
All right, ready?
This is supposed to be a movie to show that, in fact, the water is clean and has no organics. It's an ultra, no metal, no organics in the contamination. There's an ultra purity. We also have a device that takes up, that uses 200 grams of MOF and delivers 5 liters of water every day. This is an electrified device, unlike the one that is deployed in the desert that is only operating under ambient sunlight, no electricity. But you see here, this works in the same way I just described. The air touches the MOF extracts the water from the air and collects it, and then when it's full, it gets heated, and then the water condenses, as you see here, accumulating at the bottom of the device, and you deliver 5 liters of water every day from 200 grams of MOF. If you want more, you can use more. If you want more water per day, you can use more MOF. And this is something that we are doing here. Here's a device that uses 2 kilograms of MOF and can give us 22 liters of water per day. So we can take up more water into the pores by modifying the linker. And here by adding 2 carbon atoms into the linker, we can take up 50% more water. And again, the device would deliver 50% more water per cycle. So that's really the power of this chemistry. This is just data that shows that the material is cyclable even with those 2 carbon atoms taking up 50% more water. It behaves in exactly the same way as the original material, except it takes up more water. Okay, so how does this look at scale? For 1 ton of MOF with no electricity, no energy input aside from ambient sunlight, 3,000 liters of water per day at 1 cent per liter, okay? No energy input aside from ambient sunlight. For the plugged-in device, for 1 ton of MOF, it will deliver 60,000 liters of water per day. Every day, we are grading this for 6 to 7 years at less than 2 cents per liter. Okay, so I think that we are slowly reaching a level where this is going to be widely commercialized. Okay, let me now spend the rest of my I showed you how the materials work, how they're addressing climate problems, but this process has taken us 30 years, and it doesn't have to. Okay, we've gone from molecule to material, engineered the material, integrated into a device, and I showed you prototypes that work. And it took us a long time. So right now we are building what we call the AI discovery cycle. Is that there is no need for this to take 30 years. It could take a lot less. If we start using robotics, automated image recognition of what the robots are making, and building data sets, and then modifying machine learning algorithms so that they're chemically intelligent and can give us the conditions under which to discover new materials faster and optimize them faster than we are doing today. So this cycle, I'll show you the initial results from this cycle. But before I do that, there's one more cycle that I like to bring up, and that's a scaling cycle. Is that we can do the first cycle and the second cycle in our lab very well, but we also need to partner with industry to do the scaling cycle, where they can refine our prototypes, design the prototypes for manufacturing, test them, source them, pilot them, and then manufacture at scale. And I think this is potentially possible in Saudi Arabia, where there's large chemical industry that could really step in and help us with this. But we can do the first two cycles very well. Let me show you the result. But first, I would like to say that we've created a new institute focusing on making that AI for discovery cycle work best. And we're focusing on climate change. So here's the cycle. And here are just simple robotics for mixing molecules together to make MOFs or COFs. We look at the wells or the reactions and image them to look at whether you're making crystals or not. We focus on the products that are crystalline because we can identify them by single crystal X-ray. We build the data sets, and as I said, we modify the machine learning algorithms so that they can be suitable for suggesting conditions under which to discover new materials. And using this AI discovery cycle, we chose ZIFs as a class of materials to look at the discovery of ZIFs. And this is the conclusion of that study, is that just from the first few iterations of that cycle with intelligent modification, chemically intelligent modification of the machine learning algorithm, we could do 50% better than random or than a researcher or better than what we have been doing. And that's huge. That means we're discovering 50% more materials than we did before in a very short period of time. This doesn't take more than a few weeks rather than years. So I think that this more and more of this we will be doing and applying it to accelerating discovery and accelerating the optimization of materials for water harvesting and for CO2 capture. In principle, it could be for any property. So these are some of the materials that we discovered that in a well-farmed area, nobody has made before. And that's a result of the fact that machine learning algorithm that we're developing are very good at deviating, at exploration, deviating from the just known landscape. We also use LLMs. Zach has, in my group, has been developing the use of LLMs together with CAC's colleagues at speeding up discovery just by using ChatGPT. And there we designed ChatGPT routines to do text mining, to do image mining, to even design a supervisor that can advise the students on what they're doing. or molecularly edit linkers so that they are better at water harvesting in this case. And even we designed 7 LLMs to be a research group and do what an entire research group does. So let me just share with you results from two of these, the text mining and the research group. In the text mining, we took 250 MOF papers and asked ChatGPT through conversational language to tabulate the conditions under which those MOFs have been made. It did this whole thing in less than 2 weeks, okay? And it sounds like a long time, but that's because we actually, in this study back in 2023, we manually would cut the experimental conditions out. But now the students can do this in an automated fashion, and it takes a couple of days for it to tabulate all the reaction conditions under which MOFs were made. Now, as a researcher, I have all these facts in front of me, and I can decide what experiment to try based on facts rather than based on chemical intuition. More importantly, this goes into a data set that then machine learning algorithms could be consulting and could be using to learn from. So this can be done with 95% accuracy. And in fact, using that data set, we could predict the synthetic conditions for different MOFs in an accurate fashion. Now, for the research group, we took this cough. Okay, we targeted this cough. We wanted to crystallize this cough because we thought it will be, and it is, good for water harvesting because it has hydrogen bond donors and hydrogen bond acceptors, ideal for binding water from air. Well, it would take a student 3 years to crystallize a material like this or to make a material like this and crystallize it. But with ChatGPT, 7 LLMs working together, doing not just scientific literature search, but the analysis, the synthesis, designing the labware that is needed, reprogramming the robotic. It took us only 2 weeks to go from a non-crystalline material, see here at the bottom, to a fully crystalline material. So instead of 3-year using LLMs, we're able to reduce that time for discovery to 2 weeks. That's really powerful and is changing. We're very, very excited with the CACS team about the future because now we are foundationally changing the way chemistry is being done in the laboratory. Is that by weaving in AI, we're able to accelerate dramatically the process of carrying out the chemistry as well as the process of discovery, because now we have the means through the AI discovery cycle to explore more of that large structure, large materials space, to explore more of it and to do so at an accelerated fashion. Okay, we can do the same with porosity, again, speeding up the process from years to just weeks. We can now take papers and automatically ask ChatGPT to ask critical questions about those papers and then come up with the answers to those questions. And this is very useful for many reasons, not the least of which is that you can build databases based on just simple conversational language. So this has already been published. So if you're interested in this, I'm happy to send you the publications on all these. So in conclusion, I want to say that reticular chemistry creates materials with atomic molecular precision. We are addressing the climate problem, and AI is helping us further in optimizing these materials. And AI for reticular chemistry is lowering further the bar for everyone to plug into science and for young scholars to find it easy to do research and to get engaged in research. So finally, I want to acknowledge, in addition to the CACS team that I've already mentioned at the outset of my presentation, my students, as well as our funding agencies, and our research partners. And I want to thank you for your attention. And if you have any questions, please don't hesitate to email me at this email address, yaghi@berkeley.edu. Or if you need copies of our papers, you can find them online at yaghi.berkeley.edu. Thank you so much, and I hope you have a very successful conference. It's been a pleasure to be with you.